It's a bunch of informal printouts.
Just drop it at my office. Scrap, okay. Someone is telling me that Linda Shapiro here started CVPR. And when she started, people like she'd have to print out the manuscripts and go deliver it or mail it out to the reviewers in 1994. It sounds wild. I mean, that seems amazing, you know. Okay, let's get started. So here's a video that I thought was pretty cool. It's from this paper called Genie. Jeff Clune, who was here a few weeks ago, talked about it, but basically they threw a big generative model at a video game, and they're able to generate new video games which are controllable. And so the interesting thing about the video game, the generated video games is that they have like semantically meaningful controllable actions, even though the training data didn't have any controllable actions. Like the training data was just videos of people doing things, and then they had a generative model and they used the latent space of the generative model to control the character here, which I thought was pretty interesting. Yeah, go check it out, Genie. It's good. Okay, so where are we? We have covered policy grid, dynamic programming, model-based RL. We started on this long, confusing journey through control as inference. And then Andrew took a detour to exploration. You gotta follow the key ideas from exploration. The main thing to take away from Andrew's lecture is really optimism. Just be optimistic. Whenever you're uncertain, be optimistic. And today we're going to try to finish up control as inference and then start on inverse RL. Because I think inverse RL will tie in nicely with control. So the whole point is that today we derived policy gradient last time. We'll do a little recap. And then we can derive Euler, model-based RL, and then we'll go to inverse RL. Yep. Some logistics. Homework 2 was due yesterday. But I think you all should have some late days. Homework 3 will release today. It's going to be a model-based RL, so you'll do MPPI, MPC plus shooting and ensembles. That'll be fun. Okay, and I guess it's due on 2 weeks from now, but I think the quarter ends then, right? But yeah, you can use your late days till the 9th, I think. Yeah. Yeah. The poster session, I believe, is on June 4th. It's in the Allen Atrium. And so you can just, we'll have some snacks and posters, and we'll invite people from the rest of the department to come talk to you all. And so it'll be fun. Unless you prefer a different model, but I think that's what we agreed on at the start of the quarter, right? Unless anyone has objections. Okay. Let me find out actually. I do not know, but let me make a note so I can find out. I think the department does have printing, but I don't know if it's poster size. Somehow my lab manager manages to print things out, but I don't know how he does. And so I'll find out. Cool. All right, let's get started. So what we covered last time is we started formulating control as inference as a framework. We talked about variational inference as a tool to do this intractable posterior inference. And then we worked through a bunch of algebra when we applied variational inference to the control as inference formulation that derived policy, maximum entropy policy gradient, right? So we'll recap that really quick, but what we wanted to do was we had this framework for hard optimality that we studied in the last 6 weeks. We want to convert to a framework for soft optimality. So we introduced this like graphical model for control as inference. And we said that the optimal policy is a posterior inference query in that graphical model. And then we said, okay, the posterior inference is really hard to optimize or to compute because of this bunch of integrals in the denominator, right? And so we said we're going to use the tool variational inference instead. And then we applied variational inference with a particular choice of approximation family to this problem, and we derived maximum entropy policy. Yeah. So let's recap what we did exactly, right? So we started with the standard graphical model, and we said to have dynamics and an action prior. but we're going to add in these optimality variables. And these optimality variables are binary, so they're either optimal or not optimal. And the likelihood of the optimality variable being 1 at a state in action is equal to the exponential reward, right? And so our graphical model is basically just augmenting the standard transition dynamics with these optimality variables so that you can bring in a notion of reward into your graphical model, right? And given this graphical model, what we want is we want to get optimal agents. We want to say, what is the action at a particular state if the future is observed to be optimal, right? And so what we want to do inference over is we want to say, given that definition of optimality and that trajectory likelihood, we want to really answer the posterior inference query. What is the probability of taking an action between P at state ST, given that optimality for P to capital T is 1, right? So it's saying that imagine that you are at this time step, assuming that everything is optimal in the future. What is the likelihood of taking an action at some state, right? And so we're saying there's no optimization, there's just inference, right? And when you infer things conditioned on optimality, we'll get something that looks like maximum entropy RF. And so really what we're saying is an optimal policy is P of AT given ST and future optimality. And we're trying to find tractable ways to compute this posterior. Yeah? Everyone, this strikes a bell for everyone? Okay. So we want to compute this posterior. And essentially, intuitively, it says, given that you're acting optimally, what is the likelihood of a particular action A at some state S? Right. Okay. So why was this difficult? It's difficult because you're trying to compute a posterior. And the posterior has this like P of X. Let's say you take a simplified version of this, right? Just a latent variable model with a Z going to an X. And Z is unobserved and X is observed. And you're trying to like find the posterior P of Z given X, right? So similar to the previous thing, we're trying to find P of A given optimality and S. Here you're trying to find P of Z given X. And this is difficult because in the denominator you have P of X, which is an integral of P of X. One second. It's an integral of P of X given C times P of Z dz, right? So you have to integrate over all Z's, and that's like difficult to compute tractably. Right? And so it's difficult to compute that posterior. And so we need to find a different way to compute that posterior. And the idea behind variational inference is you have an intractable posterior. You're going to try and approximate it with a tractable posterior. So like this is when I say tractable, it means that it's like you know how to sample from it and you know how to compute KL divergence with it or like compute likelihoods with it, right? So the two things that make something tractable is that you know how to sample from it and you know how to compute its likelihood. And so we're saying let's like, for instance, a simple tractable likelihood is a Gaussian, right? So we can say that if Q Z given X is like represented as some Gaussian of like some mean and some variance, right? That is a tractable distribution. And so we're going to try and approximate our posterior with some tractable Q of Z given X.
Just out of curiosity, the fact that the original formulation requires you to integrate over all Z's, is that essentially saying if you guaranteed want to find the best actions, you have to actually look through all the states and actions?
That's right.
Okay, so that's what it's saying in English.
Yeah, exactly. Yeah. In English. Yeah, but like one way of thinking about it is that, yeah, max, like the way you'd have to look through the max is you'd have to look through everything. And like sampling is not that different. Like sampling is kind of like a soft max. It's basically saying things that are higher value will be sampled higher. And so to compute proper likelihoods of everything, you have to sample everything too. Right? And so that's kind of the thing. Okay, so we wanted to introduce this approximation, and then you wanted to minimize the KL divergence between the approximation and the true posterior. Okay? The problem with this is that the true posterior, you don't know. So how do you compute this KL divergence? Well, we did some algebra and gymnastics. We won't go back through that, but we showed that this KL divergence could be expressed as this thing we call the evidence lower bound, right? And so the evidence lower bound is like you ignore when you're trying to minimize this with respect to Q, you're trying to find the best approximation to your posterior. You really don't care about this last term. You only care about the first two terms, right? And you can think of this term as reconstruction. And you can think of this term as like matching the prior, right? And so this one is saying that like given a z, you're trying to get the x back. And this one is saying, try to make your q not diverge that much from the prior. Right? And so this is the idea behind most variational inference, variational autoencoders, and so on. But what we learned is that if I want to find the best q, I can just optimize this objective. I can just say, I want to find the max q, optimizing this objective where every entity is known. Right? So you don't have to ever compute this integral in the denominator. Like, you know how to sample from x, that's your data. You know how to sample from q, that's your tractable posterior. You know the likelihoods, right? Because that's the thing you're trying to find the posterior of. And you know the prior. And so everything is known, it becomes easy to compute. You just learn like gradient descent on it, right? And so that's what variational inference is. Does that make sense? Like, basically we're trying to say each tractable posterior approximated with a simple tractable approximation, and do some algebraic gymnastics, and you get like this evidence lower bound. Evidence lower bound is reconstruction or maximum likelihood and staying close to the prior. Is that parse, Fabio? Like, if you didn't parse, the main thing to remember is that we introduce an approximation q. We solve this objective to make q close to p. Okay, so that's what variational inference was. And we just need to learn a tractable posterior q, where we know the likelihood, we know how to sample from it. Right? Okay, so this is posterior inference with variational inference. And we said we have this difficult problem of inferring this in the policy posterior, AT given ST and future optimality. And we want to figure out how to do this using variational inference. We said as the integral in the denominator is kind of a pain, but can we use variational inference to do this? Does anyone remember how we would, like, what is, like, if we, oh shit, okay. I will reveal the answer if I go to the next slide. But if we like just took an analog to z and x, right, and we just wanted to reapply the evidence lower bound as is, just to pattern matching, which ones are x and which ones are z? Like, what does z correspond to here and what does x correspond to? Yeah, go ahead.
The z would be the states and actions, and x would be the optimality.
That's right. Z is states and actions, x is the optimality variable. Perfect. And so you're going to like have x being the optimality variable, z being the states and actions, and you're going to like directly try to like find out the expression for the evidence lower bound, substituting x as optimality, z as states and actions, and we know the like likelihoods in our controller's inference model. We know that optimality is proportional to or like equal to xr. We know that this thing is according to the transition dynamics. We know that this is according to action prior. So we know those things, right? And we're going to substitute them in to get our variational inference expression. That's a good question. So you can't actually, like, the way we're going to get this is we're gonna like include s's and a's all inside z, but the factorization inside, like, we're gonna have like a factorization of q into a bunch of like different product terms, and some of them will be conditionals like a given s. So the reason you can't observe z is because you don't know what states are optimal, right? And so like states affect future states, and so you can't treat that as observed because you don't know which things will lead to optimality. Right? And so what we're going to do instead is we'll like treat z as like all the states and actions, but we'll factor it into a conditional probability distribution like an a given s, which will let us take actions like a policy. Right? But you basically can't observe what states are in there because you don't know which is optimal. Yeah, it's a great question. Yeah, I thought of that myself when I was writing this up. That's a good question. Okay, any other questions about this? So what we've done is we've said controller's inference is standard graphical model with these additional optimality variables. That's it. That's hard, and a policy is posterior inference. Posterior inference is hard to do. We're going to use variational inference. In variational inference, the observed are optimality, the unobserved are state and action. That's it. Yeah. Okay. And then let's do a little bit of algebra here, right? So what we're going to do is we're going to choose a particular form of our q. Right? So if you remember our q, it's a q of z given x. In our case, Z is states and actions, X is optimality. That's a Q of states and actions given optimality, right? And so we're going to choose a particular form for this Q. It's an approximation. You can choose whatever form you want. And our form is going to be a product of the initial state likelihoods times the transition likelihoods times a Q of AP given ST, which is basically your policy.
What do you, like, what does that entail? What is another form of Q?
Like, that's a good question. Like another form of Q is just like a big neural net, which takes in O0 to T and outputs the mean and variance over states and actions, right? So it's like, it's a probability distribution. And like, there's certain, in any probability distribution, certain parameters you can vary, right? And so here, what we're choosing to vary is we're saying that we're only going to vary that Q of AT given ST, and everything else is going to obey this, like the initial state distribution and the transition dynamics. But the only thing you're actually going to vary in here, the parameters of your probability distribution are just the Q of AT given ST. And so it's like imposing a little more structure onto your probability distribution. So it's saying it's like, it's not an arbitrary probability distribution, it's one that is constrained to obey the transition dynamics. And the reasoning behind that is that you want your policy to obey the transition dynamics. So you don't want it to like choose its own transition dynamics because it has to run in the world. Right? That's the point.
It's hard for me to see any other formulation. Because it's like you roll out and then
Like one thing you could do is you could have like neural net, which takes in optimality, right? And then you have like neural net, whatever. And then output is mean variance over states and actions, states and actions, right? So it's like, it's just a standard Gaussian. You can imagine that you had like, you have a probability distribution that takes in optimality as input. Plus the neural net outputs the mean and variance over states and actions as the output, right? That is like a valid choice of approximation. It's not a very useful one, but it's a valid choice of approximation. Okay. Yeah. So we still want to answer the posterior inference query of like, what are the likelihoods of actions and states when everything is, when the agent is acting optimally, right? So that means like you want to do things that maximize the reward, which is when you're acting optimally. For this Q function, we're always going to query it when the optimality is 1. Like you don't care about suboptimal behavior. You only care about optimal behavior. So you can like kind of drop this. That's why if you look at the right-hand side, there's no like condition on optimality because it's like, it's always 1. So you don't need to condition. Okay. So we've said that's the evidence lower bound. That's what X is, that's what Z is. This is our choice of Q, right? And we're just gonna like stick in this Q into this evidence lower bound. That's it, right? And it's going to magically give us maximum entropy RL. Do you want me to go through the steps again, or should we just keep moving? Yeah. Okay. So there's a bunch of steps. Basically, you just like substitute that Q in. You work through some algebra, and the initial state distributions and dynamics cancel because of your choice of variational approximation, your choice of Q. And what comes out is essentially maximum entropy RL. So it's saying that the evidence lower bound reduces to this objective, which is an expectation where you're sampling initial states, sampling actions from your Q, sampling next states from your true transition dynamics in the world. And then you're maximizing this, or then you're maximizing the sum of rewards plus an entropy, right? And so that's exactly maximum entropy RL. And note that it's all in the real world, that you're like sampling from the real world, you're only taking actions from your policy, right? So this is literally the same objective that we derived in actor critic or in policy gradient. It just has an entropy term in it. Yeah. And so the thing that's cool about this is that we started with posterior inference. Our goal was posterior inference, right? We want to answer that query up there. We said posterior inference can be approximated by like the variational lower bound, evidence lower bound. We chose a particular choice of Q. You ran through all this, and then you get maximum entropy RL. And so the evidence lower bound is maximum entropy RL. That's what we're saying here. And if I want to like, now I have a lower bound, I just want to, we know that choosing the best approximation is maximizing that objective. So you just want to maximize that objective. And so choosing the best approximation to posterior inference is the same as solving maximum entropy policy gradient. And so all you need to do is just do maximum entropy here. Just do like max Q over here, which is just like solving the policy gradient problem with entropy added. That's all. Okay, so that's the first thing we showed. Posterior inference gives you the optimal policy, and when you approximate it with variational inference, it amounts directly to the evidence lower bound amounts directly to maximum entropy R objective. And what we did last time is we said, you want to maximize this thing, just do gradient descent on it. Right? And the simple way to do gradient descent is just go back to our third lecture and do policy gradient. Right? Just do policy gradient with an additional entropy term. That's it. And the entropy term is easy to compute because it's just on your policy. Right? You just do a little bit of chain rule in there. But the point here is that we've like derived policy gradient, and now we'll go and derive Q learning and model this stuff. But it's like the main point to remember is optimal policies are posterior inference coins. This is one choice of approximation, which is variational inference plus gradient descent. You're taking subjective evaluations. Okay. Everyone kind of buy that? Questions? No? Okay, good. So what we showed is that maximizing the elbow with gradient descent is equal to maximum entropy policy gradient. And what we're going to show in the next two sections is you can do a similar set of algebraic gymnastics to get Q learning or soft Q learning. And you can derive model-based RL in a similar way, like algorithms like MPP. And then we'll talk about inverse RL, and this stuff will connect to inverse RL in a bit. Okay, let's get started with Q learning, right? So we took this elbow and we said that the evidence lower bound, that objective, with this choice of Q, gives you this maximum entropy RL objective. Right? And we said we're going to, if we solve it with gradient descent, you get policy gradient. Now, what we're going to try and do is we're going to try and solve it with dynamic programming. And if we solve it with dynamic programming, we're going to get soft Q learning. Right? And so we're just going to take the same objective, maximizing that thing, and we're going to show that solving a dynamic programming will give you a different algorithm. Okay. So how many of you are familiar with LQR? Yeah. Are you familiar with how you derive the Riccardi equation? And so you go backwards, and you go backwards and you like optimize every step. Something similar, right? So what we're going to do here is we're going to say, this is our objective. We want to maximize this, right? So let's start from the last time step. Sorry. Let's start from the last time step. And so the last time step only has, like, it doesn't have any dependence on the past. It says states are sampled from some Q of ST. Your actions are sampled from your policy. You have your terminal reward, R of ST 80, minus log Q, which is just your entropy. Right? And so you want to find the best Q of AT given ST at the last time step. So you're trying to find the best Q of AT given ST, right? And we're going to try and like massage this into a form where it's easy to do. You can blast this with gradients if you want and try to find the best Q of AT given ST. We'll just try to find an easier solution to it. Okay, so here's one way to do it, which is log x of x is just x, right? Of any x. So we're just going to replace r by log x of r. And this is just going to help us massage terms together. But like essentially log x of r is equal to r. So I can just replace r by log x of r. Yeah. Okay, so that's the first step. The second step is we're going to add and subtract something, right? So what I'm going to, like the intuition is I'm going to try and convert this into a KL divergence. And if I can convert this into a KL divergence, I know that KL divergence is always positive and it's like minimized at 0. And so if I can convert into a KL divergence, I know that I can find the best Q. If I can convert a KL divergence between Q and something, I know that the Q is minimized when it's equal to that thing. Right? And so I'm just going to try and I'm going to massage it into a KL divergence. That's what I'm trying to do. Right? And so whenever what we're going to end up with, just to like preview, is we're going to end up with Q is like proportional to X R. But we're going to derive that just by trying to make it into a KL divergence. Okay. So what I did is I converted into log X and then I subtracted log x, and then I added log x. Or log, sorry, I subtracted log integral x, and I added log integral x, right? So the reason to do so is because if I like have x bar and I want to like normalize it to a proper probability distribution, I need to have like an integral x bar. Okay. You don't actually need to follow all of this. Just get the vibes, you know. Okay, so you're just going to add and subtract, and then you're going to do you're going to say like log a minus log b is equal to log a over b, right? And so you're going to take this term and this term, and you're going to get log of x bar by integral x bar, right? And for now, this term doesn't matter. The second term doesn't matter when you're trying to minimize q because it doesn't depend on q, right? So we're just going to ignore it for now. That's why I've dropped it in this term. And so all we've done here is we've added and subtracted, and then we've done log a minus log b is log a over b. But now the nice part is that this is a proper probability distribution because it integrates to 1, right? That's positive. And if you like look at this carefully, this starts to look like a KL divergence now, right? And I'll do one more step. Again, you can say log a minus log b is log a over b, right? So it starts to look like log of q over x bar divided by integral x bar, right? So you just like, this is, consider this to be a, consider this to be b, and then you get this as log a over b. That's it, right? And so all that we've done here, and now this, and if you remember the definition of a KL divergence, a KL divergence between p and q is p log p over q, right? And so we can show that this expression right here is exactly the KL divergence between q and x bar divided by integral x bar, right? And so what this suggests then is what would the minimum q be? So just to recap, all we've done is we started from this thing, we did log x, we added and subtracted something, then we did a little bit of algebraic rearrangement with the logs, and you got a KL divergence between q and x bar divided by integral x bar. So what is the best q? Oh yeah, go ahead.
So for the second term, x bar divided by integration. Is that like kind of like south?
Yeah, it is softmax. Yeah.
So essentially, you just stack the term.
Usually softmax is over a discrete set, and this is over an infinite set. But in that sense, it's like a softmax over an infinite set of states and actions.
Then the have to as close to that infinite set of stuff.
No. So one way of thinking about it is that this like if you only had a finite action space, okay. If you had a finite action space, this integral is just a sum. If you have an infinite action space, this integral is an integral, right? So it's just like saying q has to be close to some true probability distribution. And probability distributions have to be normalized. And so just saying q has to be close to the normalized x bar. And so it's easy, like if it is discrete, q would be equal to the softmax. And if it is not discrete, q has to be equal to this like normalized energy or normalized x bar.
Oh, for the Q question?
Yeah.
There's a max, and then we have a negative inside of the expectation.
Yes.
So we want.
So in the min, yes.
Q to be as close to the thing on the other side.
That's right.
So then it should, from the state, predict, from a state in action, it should predict reward, basically. The reward, distribution of reward should be the same as the.
I think the answer might be even easier than that, right? It's the answer might just be that the KL divergence is, or the answer is that the KL divergence is non-negative, and it's minimized when p is equal to q, which means that q is just equal to x bar divided by integral x bar, right? And so this is over actions, right? So this thing that on the right hand side is a probability distribution over actions, right? And so it's saying that like the q is equal to exponential return or reward divided by integral exponential return. And the main point is what I was saying, Andy, is basically you can't say q is equal to x bar because it's not a probability distribution. Like you have to say q is equal to x bar divided by integral x bar. So that's a valid probability distribution over actions, right? So you can think of this like intuitively, right? What it says is that like for rewards that are high, like your q will have higher likelihood. Rewards that are low, your q will have lower likelihood. So essentially it's like a soft max, like like Andy was saying, but it's like a continuous softmax, not a discrete one. Right? But it's like, imagine that the rewards were scaled by 1,000,000, right? The things that are really high will occupy all the likelihood, and the things that are low will get no likelihood and becomes the hard max, right? So like we know in Q learning, for instance, it would be like the last time step would choose the max, right? Here, what we're doing is we're choosing the soft max, and the soft max is just like it's not collapsing all the likelihood to zero. It's a max you collapse everything, soft max you don't. You have some likelihood, but it's proportional to how high the reward is. Right, so that's why in maximum entropy RL, like scaling is an important thing. So like remember that you like scaling will change how close it is to a max. Like if you scale the rewards really high, like exponential will take scales and like blow them up, right? And so it'll like go closer to a max. Okay, but intuition here is that we did some gymnastics. We took the last time step, converted into a KL divergence, and then the KL divergence is minimized when p is equal to q, so q is equal to x bar by integral x bar. So equal to soft max over terminal rewards. Okay. That's right. Oh, because we're trying to do maximum over q. There's no q. I'll add it back in a second, but I just didn't want to have it on the side because it confuses. Right, so it's basically, it doesn't depend on Q, but it will determine what the maximum value of this thing is, right? And so then, now that I know that Q is equal to x bar by integral x bar, when I substitute, when I want to find the value of this expression, I don't want to find the argmax, I want to find the max. I will have to have that expression, right? So like, I dropped it for the sake of finding the argmax, but I have to like have it back when I find the max. Yeah. Yeah. Here? Here? Yeah. I guess it should be this and this, right? Yeah, it's like this whole, let's call it this whole probability distribution P. And so it's like Q over P.
Right. So
it's just my bracketing is a little weird.
It'll give like sum of Q times log Q because it's an expectation. Oh, I see.
Okay, so what we've kind of derived here is that the policy, the optimal policy is equal to the softmax over the terminal rewards, right? And in the last time step, let's call our terminal rewards Q. Okay, just discussed. And we're gonna call this expression log integral x r or log integral x q in this setting as d. Okay, and I'll tell you why that makes sense in a second. Because at the last time step, basically the q function is the reward function. There's no future values, right? So the q function is the reward function. And this thing, like normally the value function is the max over the q function. This is the soft max over the q function. Right? So this is the same way that I was saying there is like, this is the value function is the soft max over the q function. And what that suggests is that if you substitute these definitions into this expression, right, you'll get the numerator becomes exp q, right, and the denominator becomes exp v, right? So like v is equal to log integral x, so integral x is equal to exp v, right? So the numerator becomes x q, the denominator becomes x v. Oh. And your policy is now exponential of q minus v, right? And so, and a lot of you might refer to this as advantage, right? Like we covered this in policy gradient and other things like you're subtracting a baseline, right? So you're saying that your policy likelihood is equal to the exponential advantage, right? And so you can think of this as like, and we'll show that this like holds for other time steps too, but in the last time step, your Q function is equal to your reward function. And your value function is equal to the softmax over Q. Oh no, my thing isn't erasing 1 sec, sorry. Sorry, I have to reshare. Give me a sec. Okay, see that. There we go. Okay, so what we showed is that in this last time step, Q is equal to R, B is equal to softmax over Q, log integral x Q. And that leads to the policy being equal to the exponential Q minus V or the exponential advantage. Right? Again, it's like, if you think of the advantages, how much better is this action than the average action, right? Then you're saying that your like Q likelihood is equal to like the exponential of how much better that action is than the average action. So it's saying that like things that are better will be weighted high, things that are worse will be weighted low.
How could the past be on?
Oh yeah, so this is x. So this numerator is xq, right? Because we just substituted. And now imagine now you just take this expression and took exponential on both sides, right? An exponential of log is equal to just x. Exponential log x is just x. Exponential and log cancel out basically, right? So like exponential of log of x is equal to x. So take exponential here, take exponential here. These two cancel out.
Oh, I see.
Yeah. And so you have like exponential v is equal to integral exponential r. Okay, so yeah, so the point here is that we got what the optimal policy was at the last time step. Intuitively, it makes sense. It's like a softmax over the Q values, right? Or it's like higher for things that have higher rewards and lower for things that have lower rewards, but also equal to exponential advantage. Yeah. But at the last time step, Q values and rewards don't really make Q values and value functions don't make sense. So let's go to the second last time step and it'll make more sense. But all we did here is we did the last, like just like we do in LQR, we did the last time step of our Riccati equation, or last time step of our dynamic programming update. We just converted into a KL divergence to make it easy. KL divergence gave us Q is equal to x bar by integral x bar, the softmax. And then we just like, to make this a recursive equation, we just define what Q and V are. Okay. And we'll derive the second last and it'll become a nice Spellman equation in a second. Okay, so all that this tells us is what the optimal policy for the last time step is, and it's equal to x q minus v. Okay, so the other thing we need to do is when we're considering the second last time step, you don't just need the argmax, you also need to know the value, right? You need to know what this expression is going to be when q is equal to the optimum, right? So if you remember, we like added and subtracted this thing, and I dropped that extra term just for convenience. You have to add it back because it's not 0. And so the expression here is going to be the KL divergence between Q and softmax over R plus log integral x bar. Okay? Because that's the term we added and subtracted. Now, we know that at the last time step, if you're acting optimally, that KL divergence is 0, right? We derive the KL divergence to be 0. And if you remember our definition of V, it's literally log integral x. That's literally what V is, right? Which means that given that our Q is equal to xq minus v, or xr divided by integral x bar, this whole expression just becomes the expected value. So just saying that this KL divergence is 0. This is the term we added and subtracted, right? And that is literally our definition of V. So at the last time step, R minus log Q at optimal becomes equal to the expected value of V. Right? That's just like the way you do it in LQR, for instance, is you like this would be a quadratic, right? You like substitute in the optimal action and you would get the last time step to be a quadratic, or in that case, it would be 0 perhaps. Right? So the point here is that the last time step, we found out what the optimal action was, x q minus v, or x bar minus integral x bar, or x bar divided by integral x bar, and we found out that the value is going to be the expected value function, where value function is defined as log integral x cubed. Right? So this is all we need to remember at the last time step. This is the policy, and this is the value. Right? So it's like we're computing this expression, at the last time step, this is the optimizer. And if you use this optimizer, this value becomes equal to the exponential or the expectation over the value function. That's it. Yeah.
That I've seen the advantage function being used like in the last few years. It's become more. That's what the graphics.
No, I think if you look back at like Sutton and Bartow's books, for instance, I think they talk about the advantage of it. So it's pretty well known, let's say.
This particular form, like exponential.
Oh yeah, like this I guess this whole field of like soft optimality. I wouldn't say it's new, but it's become popular in empirical deep RL in the last few years. Like it is like Todorov, who used to be here, did a lot of work on this, and but I think that was just a different community. Like I think optimal control and like LQG and stuff do things like this often.
Does this work better than
Yeah.
when you assume this particular form?
It works like this form is exactly the same as if you remember like soft actor critic, right? Like you can derive soft actor critic from a similar perspective, and those algorithms do work better. So the algorithms that work best in practice have like they're derived from this kind of perspective. Yeah, in 2 or 3 slides, I'll show you how it's gonna happen. Yeah, it like matters in practice, yeah. But maybe not for the same reasons that they were derived. Yeah.
I know how the exponent got there from all the formulation, but I'm just curious, like, what purpose does it serve? Like, if we just took out the exponent, did something else to make sure it was like a, I don't know, valid distribution, like why the exponent?
So one reason is that it's always positive. So it's a probability distribution. I think it all comes from the way that you define your optimality variable. Like if you chose a different monotonic positive function for optimality variable, you'd get a different choice of policy. Right? I think it just really depends. It just really comes from our choice of the probability distribution for optimality. I think it just like works out to be convenient because it matches what we do. The KL divergence uses the log and the x. We use the KL divergence at work. So I think you can change it to a different function. I just like not. I haven't worked it out immediately to remember to know what to do.
It seemed like the advantage squared is like the loss or after in advantage actor critic, I think. So I maybe I'm misremembering, but
It's usually the Bellman error square, which is it's not quite the advantage there. Okay, so that's the last time step. That's your optimal policy. That's the value, right? And now let's go to the second last time step. So the second last time step, we're gonna have a little bit more, right? So if you just remember what we do in elsewhere, it's kind of the same thing. You're gonna have your second last report, an entropy at the second last time step, plus the last time step, right? So this is the second last time step, these two, and that is your last time step. Okay? And you're gonna like sample the second last time step from Q. You're gonna sample the second last AT minus 1 from Q of AT minus 1 given ST minus 1. And then you have your last time step acting according to Q of AT given ST and so on, right? So this is the last time step that we computed earlier, right? It's going to be optimal. And now we're going to like try and compute the second last time step, right? That's just what dynamic programming will do. So help me work through this. What did we compute as the value of the second last time step? Expectation of value, perfect, right? So it's just going to be expectation of value. So all that we did in the last time step was, all that we did in the last time step is we computed this expression, and we said that it's exactly equal to the exponential, the expectation of value, right here, right? And so we're just going to substitute that in the next equation, right? So we've said this thingy on the right-hand side is just equal to the expectation of value. That's it, right? And you're saying the last time step is acting according to the optimal Q, the best Q. And so this thing is now going to be expectation value. Now we'll do a little more funny business, right? We will call R plus expected V Q, right? Just like we did in the Bellman equation, we will like, let's say that at the second last time step, at the last time step, we said Q is equal to the reward, right? There's no future time steps. But at the second last time step, let's call Q reward plus expected value in the future. Expected value in the future being E of B, right? So we're going to say that we're going to define Q function as current reward, plus expected value in the future. Right? And that's literally your Bellman equation. That's literally what you did in your Bellman equation. But if we define this thing as Q, then you can rewrite the expression, this expression above, right? You'll just call this thing plus this thing as Q, right? And so you can rewrite your expression as the expectation of Q minus log Q, right? So all we've done here is we've said R plus expected V is Q. And then we've said that we're just going to substitute that back into the second last time steps equation. You'll get the expectation under Q of Q minus log small q, right? Just by definition of what the Q value is. Now, if you do pattern matching, this looks exactly like the form we did in the last time step, right? In the last time step, we had this expression, right? We had this expression, you had R minus log Q. Now we have Q minus log Q, but it's like the same form, right? And so we're just going to do pattern matching rather than struggle through the computation. So we're going to say like this looks exactly like the last time step, right? And at the last time step, we just derived that Q of AT given ST is equal to X R divided by integral X bar, right? Here we're going to get Q of AT given ST, or AT minus 1 given ST minus 1 is equal to X Q by integral X Q, right? All we did is like, we substituted in R plus expected V as Q. This looks exactly like the previous time step, just with Q instead of R. So every expression should be the same, right? And so just with Q in place of R, right? And so what that is going to give us is that our optimal policy is equal to XQ minus V, where V is equal to the log integral XQ, and Q is equal to R plus expected V in the future. So this is the substitution we did to get this thing. We said R plus V in the future is Q. And then the same way that we did last time, we defined the value function as log integral X R in the last time step. Here we do log integral X Q, right? And so the point here is that your optimal policy again is X Q minus V. And your V is defined as log integral X Q, the softmax over Q. And your Q is defined as R plus the future. Right? And so now it starts to look a little bit like our Q learning equations. It looks like a bit like our Bellman equations, in the sense that at our second last time step, we're just going to do dynamic programming. We're going to say that the Q is equal to R plus future V. We're going to say V is equal to the softmax over Q. And then the policy is equal to XQ minus V, the exponential impact. Okay. So in Q, I'll connect Q learning in this in a second, but Q learning is very similar to this. It's just with maxes. Like this is a softmax. This is a softmax. In Q learning, the policy is max over Q. And the value function is max over Q. Right? In soft Q learning, the value function is soft max over Q, and policy is soft max over Q. Right? And so the only difference between Q learning and soft Q learning is one is like soft, which means that you do log integral X, and the other one is max. And if you like have a temperature term or you do scaling Q, like soft will become hard. Right? So if you like multiply all your mores by 1,000, like your soft Q learning will become hard Q. I'll work that out in a second. Yeah, that's a great question. So usually what people will do is like it's useful to have softness, and it's at the start of training. And so they'll have a constraint that your entropy should be higher than some number. And then they do like a constraint optimization. Like in soft actor critic, they'll say you want to maximize. Some people will have like a weighting term that they opt like hyperparameter use for, and others will have like a constraint that they adaptively adjust.
What is the constraint?
You just pick a random number. Yeah, heuristics. It's a good question. Okay, so that is the second last time step, but you can just like extrapolate from this to more time steps before, right? So it suggests that the base case, the last time step, Q is equal to R, and V is equal to log integral X bar, right? That's the last time step that we derived. And then for every time step before, you're going to say that Q is equal to R plus expected V in the future, right? And you're going to say that V is equal to log integral XQ, the softmax over Q. And then the policy is equal to XQ minus V, which is essentially the same as XQ divided by integral XQ, right? So like Andy was saying, I don't know where Andy went. There. This is softmax. This is the softmax over here. Right, and so this becomes just like a Q-learning update, right? It's just saying that you did dynamic programming, you worked on the path. Your optimal policy was, or your Q function is R, log integral x bar, softmax over R. And then every step before you go do the Bellman update, so Q is equal to R plus future B. B is equal to the softmax over Q, and your policy is equal to the softmax. Now, it's not exactly the same as actor critic, right? So an actor critic, you have a different actor and a different Q function, and you try to evaluate the actor and the Q function. Here we're doing something more like Q learning. We're doing the max, right? In Q learning, we did the max. You don't have any actor. Here you're doing like the soft max, right? But there's no in some sense, the policy is just like implicit in the Q function. Right? The policy is just the normalized exponential the Q function, which is like the soft max over the Q. The same way that in Q learning, the policy is just max over Q. In soft Q learning, the policy is just the soft max over Q. So the policy is fully implicit in the Q function. Right. And one thing that's tricky is when it's continuous, you have to get an integral, which is a pain. When it's discrete, it's very easy to compute the softmax. And so that's why soft Q learning is hard to use for continuous spaces. But soft actor critic is easier to use for continuous spaces. But the point here is that we have a soft Bellman equation. So this was our original hard Bellman equation for Q learning, right? We said Q was R plus expected value in the future. V is equal to max over Q, and pi is equal to arg max over Q, right? And in soft Q learning that we just derived, again, Q is equal to R plus expected value in the future, but your value function is your soft max over Q, and your policy is your soft max over Q, right? And so the only difference here between Q learning and soft Q learning is that this is hard max, this is soft max. And if you set this alpha to 0, the soft max becomes the hard max, right? And so I think that's kind of neat because we basically took the same evidence lower bound that we derived policy variance from, and we just solved it with dynamic programming rather than with gradient descent, and then you derived soft Q learning, right? And so you still started from posterior inference, variational inference, evidence lower bound, but you solved it with a different optimization tool, which is dynamic programming, and you got a different algorithm, right? And one of the algorithms that we studied already. Now in practice, you often use soft Q learning or soft actor critic because it like helps in different ways. It like helps in, it like makes optimization better. So there's nice paper on the theory of policy gradient methods you should read. It's like talks about why entropy prevents like gradient collapse. There's also things about like if your rewards are wrong, or your problem is misspecified or noisy, like entropy helps. And for transferring across problems, like you optimizing a maximum entropy objective can be helpful, right? So the main point of this exercise was to derive Q learning to show that Q learning and policy gradient are like two sides of the same coin, right? They're just like different optimization techniques on the same objective. One is dynamic programming, one is brute force gradient descent. So one is using the temporal structure of the problem, one is not, but they're optimizing the same objective. Yeah. So we haven't covered SARSA in class, but all that SARSA is it's saying that it's a non-off policy version of Q-learn. Right? So it's saying that instead of taking SA S prime, you take SA S prime A prime from the data set. And so you never have to sample in Q-learning the target, you sample A prime from your policy. In SARSA, you just sample from your data. That's it. And so everything else should hold, right? So you can derive the same. Okay, so what do we do here? We started from the posterior inference query that we converted into the evidence lower bound. We said we're going to do dynamic programming. Dynamic programming gives us essentially the soft Bellman update for soft Q learning, which is the Bellman update, soft max, soft max. That's it. Okay, any questions? Are we lost? Or do we feel pretty good about it? Yes? Okay, I don't know. The first time I learned about this, I thought. But I think the point here is we started from this controllers inference framework. We showed policy gradient, and we showed Q learning. They both come from the evidence lower bound, just different approximations. Now, model-based RL does not exactly come from the evidence lower bound. We'll still do posterior inference, but in a different way. Yeah. And so what we'll next have model-based RL. I think actually we won't get to inverse RL till Monday, but let's go through model-based RL. Yeah. Okay, so what we did in posterior inference for policy-graded and Q-learning was we said that we're gonna we still want to sample from the world. We don't want to sample from like some model. We want to sample from the world, and then we want to like construct an evidence lower bound where optimizing it involves sampling from the world. Right. So if you remember our, do I have it here? No. If you remember our like evidence lower bound, if you notice that this is all like sampling from the world, right? So when I say sampling from the world, it's like sampling from P, and P is like the true environment, right? And in RL, we have access to samples from the true environment, but we don't have access to the like functional form of the true environment. So what we've done here is we've had to like sample from the true environment. But in model-based RL, we want to like sample from a model, right? We want to like learn a model of the world and sample from that model. And so you can try and do something a little bit different in trying to do this posterior inference query. What we're going to assume is that we get a bunch of data, S, A, S prime, and R, in the true system, P, right, from the true environment, like take samples in the environment, just like we did before. And then what you're going to do is you're going to try and learn a surrogate model, P hat, to approximate P, and then use that for posterior inference, right? So we're going to still do posterior inference, but we're not going to do it against P. We're going to learn a surrogate model P hat that approximates P, and then we're going to do posterior inference in that surrogate model, right? And that surrogate model is nice because you can reset it, you can sample it whichever way you want. It's like something you have full control over, right? Posterior inference will still be hard, but at least you have like control over that. Whereas from P, you can only draw samples. You can't like reset it to wherever you want. You can't get likelihoods. You can't get those kinds of things from P. You can only get samples from P, right? And so what we're going to try and do is we're going to learn a surrogate model P hat, and then we're going to use it for posterior inference. And we're going to show that gives us model-based RL. Okay. So the first step is, how do we do learning of a surrogate model? And I think the easiest way to do the learning of the surrogate models is through maximum likelihood. Right? And so if you remember from earlier, maximum likelihood often involves something like this. Let's say you were trying to do maximum likelihood for some function y given x. You're going to say, let's sample x and y from your data, right? And then you maximize the log likelihood of y given x under some model p theta that you learn, or let's call it p hat theta. So in maximum likelihood, you try to optimize that objective. That you're saying maximize the likelihood that the data x comma y was produced under your model p theta. Right? And so we're going to do, and that is the same as supervised learning. Maximum likelihood is equal to supervised learning. Right? And so what we're going to do here is we're just going to do maximum likelihood, but between the true p and our model p hat. Yeah, so p hat is going to be our approximation. So imagine that we had this like this graphical model. We're going to construct a clone of it, and we're going to try and fit that clone by minimizing the KL divergence between those two. And like the only difference is this one, you don't know you actually don't know the probability distribution for transition dynamics and so on. In ours, we will, right? And so we're just going to like try and make these clones as close to each other as possible. And so we're going to say, let's try and do maximum likelihood, which is the same as minimizing KL divergence. And it says that let's try to minimize the divergence between P and P hat. P hat is our model, P is the true environment. So this is just the same as supervised learning or maximum likelihood. Don't be fooled by the KL divergence. The KL divergence is literally the same as maximum likelihood. And the reason for that is if you're ever doing expectation P, whatever, log X, right? You can just like, I'll skip it for now. But basically you can show that the KL divergence is equal to the maximum. And so if you kind of work through the steps here, if you write out the maximum likelihood expression and say, take samples of states, actions, and optimality from your environment. So like just take samples in the environment and maximize the likelihood of those samples under your approximate model P hat. Right? So your P hat is your approximate cloned model. P is your true model, right? True environment. And then you like, don't take samples from the true environment, maximize the likelihood of your fake model, that's a approximate model. And if you just like work through a little bit of algebra, you're going to factor P and P hat the same way. So P, if you remember how P was factored, right? P of S naught, A naught, blah, 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 optimality, blah, 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 is equal to product of the initial likelihood times initial transition dynamics times the action prior times the likelihood of optimality, et cetera, right? You like multiply all the terms times stuff like that stuff. And so we're going to do the same thing. Right? So you're going to take the product of the initial state and transition dynamics times action prior times optimality. Right? You're going to multiply that time step over time step. And so what that's going to give you in a long-winded way is you're just going to get model learning, right? So you're going to say that this objective is going to break up into 3 terms. Okay? The first term is estimating the initial state distribution. The second term is estimating the transition dynamics, the same thing we did in model-based startup. And the third term is just estimating the reward. And so all that we're saying is that we're going to learn 3 models, one which is the estimate of the initial state, second which is the estimate of transition dynamics, and the third which is our estimate of our reward. So all that we did here is we start from maximum likelihood from KL divergence. We show that that's equal to model learning. So just this is the same as we did in model-based startup. We just add a reward learning. We just do regression. So that's it. Nothing fancy. So what I'm trying to get at here is like fitting an approximate p hat amounts to just doing supervised learning for your dynamics and your reward. The same thing we did model-based startup is just the same as like minimizing the divergence between a clone p hat and your true model p. They're the same. Yeah. So like you're going to do in your homework, like fitting your model is just like minimizing mean squared error between your predicted next state and the true next state. And predicting rewards is going to be, you're going to have something that takes an S and A and gives you a scalar. You're going to try and minimize the distance between that scalar and the true reward. Okay. So that's the first thing we did. We said we've learned the model. So we've gone from this like model that we didn't know to a model that we do know, right? So like the problem here is that we can sample from P of ST plus 1, and we can get rewards on running things in the environment, but you don't have likelihoods, you can't optimize for them, right? Here we have a model P hat, and P hat, you know the likelihoods, you know the rewards, you've learned predictors for it, right? So you just make like a fake model that approximates the true model, right? And then what you can do is you can just do like posterior inference in your fake model, right? So the same way that we did earlier, is we're going to say that we're going to pretend that our fake model P hat is our true model. And we're going to try and do posterior inference in our fake model, right? So the same way that we did P of AT given ST and optimality in variational inference, right? We're just going to do P of AT given ST and optimality under P hat, right? So you're still answering the same posterior inference query. You're just doing it under P hat. And you fit P hat to be the same as P by minimizing the divergence between this joint likelihood and that joint likelihood. So minimizing the divergence between the joint likelihoods is literally model learning. And then you're going to like pretend to do posterior inference in P. Right? You don't have P because you have to sample from the true environment, but you can do posterior inference inside P hat. Right? So just like we did in policy grid, just like we did in Q-learning, we're going to do posterior inference, but we're going to do it inside P. And the nice part about P hat is we know the model, we know the functional form of our model in P hat. We know everything. It's not just that you can sample from it. You like know the likelihood, you take grading, so you can do all sorts of tests. Right? Yeah.
Would you still need that, like, the same as me?
Yeah, that's a great question. We'll get to that. Like the answer is yes and no. Like yes, as in like you can do that, but you don't have to do that.
What if that's because you're saying it's actually optimally, but in the previous slide you have the probability for optimality, which you just say that if the action was optimal, so it's always one.
Are you saying in the model fitting part? In this part? Yeah, so you can think of this as like reward learning. So it's like when you're taking samples in the environment, you're not you're not getting optimality variables, but what you're getting is rewards, right? And so you know that log p hat, for instance, is like it's gonna like p hat is going to be exponential rewards, right? And so you're trying to fit an approximate model of rewards. So the first term is fitting your initial state distribution, the second term is fitting your dynamics, and the third term is fitting your reward. Right. So that's it. That's it. Okay. Great. So as Raymond just asked, do we still need queues and all of this like variational inference stuff? The answer is yes and no. But what we're going to do is we're going to pretend that p hat is the same as p. This idea called certainty equivalence, which means that you're like sure that p and p hat are equivalent with certainty. And so just saying that like you're going to pretend that p hat was the c. You're going to try and do posterior inference. Okay. And so as Raymond was just saying, we're going to have all of the same challenges of posterior inference, right? So the first idea is to just do variational inference like we just did. We did all of this jazz on variational inference. You just do it with p hat. So you replace all of the equations we did in the last two sections with just p hat instead of p. And you can derive.
Here's equations by Boy Things on Spotify.
Sorry. So you just replace p with p hat, and you can use the same set of equations we used for policy grid, accurate grid, just under p hat. Right, and so we talked about these methods in class MBPO and like methods that try to like do policy search in a model, right? Like by generating samples from your model. Like all of those methods you can derive by doing variational inference in p hat. Right, so all those methods are you fit a p hat first, and then you do variational inference in your p hat. And like why would you do that? Is the hope is that you need less samples to train a p hat than you would need directly in the environment. Right? So that's why model-based style is supposed to be more efficient because you can get away with less samples. But that's the idea one. This is the same thing as MBPO, Dyna, some of the other algorithms we discussed, where you're pretending your model is a simulator. You're just doing policy optimization, model-free RL in your simulator, which is your model. Right? So all of those you can derive just by doing variational inference in p hat. Okay. And the second idea we're going to do is we're going to use Monte Carlo sampling, or like if you remember algorithms like MPPI and PC, we're just going to run. We're going to do sampling in the environment, and sampling in the environment is going to give us like good actions. Okay. And so the first one is pretty straightforward. We just like do the same thing we did in the last two steps, just replace p with p hat. That's it. The second one is a little more involved, so we'll go through that. So all I've done so far is I took p, I approximated p with p hat. So that was super awesome. Then I said, I want to do posterior inference with p hat. How do I do it? It's hard to do because of the integral in the denominator and all of that jazz. We're just going to do variational inference with p hat. It's going to give us MBPO, Dyna, those types of algorithms. Or we're going to try and do some like approximation with sampling, and that's going to give us algorithms like MPPI and so on. Okay. So let's try and like this is it's not the tightest equivalence in the world. It's a little loosey-goosey, so bear with me a little bit. And so what we're going to try and do is we're going to try and approximate this posterior inference query by using the Bayes rule, and we'll get something that looks close to MPPI, but not exactly. Okay, so Bayes rule says that if you have this conditional likelihood, you can write it as the joint of A, S, and optimality divided by S and optimality, right? That's just Bayes rule. P of A comma B divided by P of B will P of A given B, right? That's it. Okay, so you have that. And now we're gonna like add a bunch of extra variables in the numerator that we're gonna marginalize out. And the logic is if you have P of A, you can write this as integral P of A comma B over B, right? So you can just like add a bunch of extra variables and then like marginalize them out, right? And so all we've done here is we've said, and the reason to do that is you have future optimality, but this numerator doesn't have future states and actions. So we're going to add in all the future states and actions and then marginalize them out, right? Because you can't know what is optimal in the future without knowing what states and actions you have in the future, right? So what we're going to do in the numerator is we're going to add in all the future states and actions, right? And then we're going to marginalize them out, right? So we're going to just say that this likelihood, just by this logic, is equal to this joint of AT, ST, all the AT and ST in the future, and optimality T to capital T. But ST and AT, ST plus 1 and AT plus 1 all in the future are all marginalized out. Right? So same logic. We just want to get it in terms of things that we know. Right? So all we did here is we did basis. Then we added a bunch of unnecessary variables that we're going to marginalize out, just so that we can get likelihoods that we know. Good. Okay. So now we know these likelihoods, right? So you can write this whole, like, we're just going to ignore the denominator for now. We're just going to say it's proportional to. We know the definition of this likelihood. We know that it's equal to the product of the optimality variable times the dynamics times the action prior, right? And so you're going to say that this likelihood, just from the graphical model that we had for p hat, is equal to initial state times the transition dynamics times the action prior times the optimality variable, right? If you just take the joint of our probability distribution, you can write as a product of condition. Just the same thing we did for p, like 10 times before. We've just done it again in our joint variable, right? And now, everyone with me? Like all we've done is we've added unnecessary variables so we can construct a complete joint. And then we factor the joint as initial state times transition dynamics and action prior times of just from our graphical model. Okay, so we've done that. Intuitively, the first term is your dynamics, second is action prior, third is optimality. Yeah. Should be this. Yeah. The action prior is the same as the original action prior that you used to approximate. Like in your model learning, I think I might have missed a term. But in your model learning, you should also have an action prior learning term. Like there should be a term that fits log p hat of AT given ST. So it's basically like what is the likelihood of sampling an action from the data collection policy? Under the simulator, yeah. Like p hat is not being simulated. P hat is just saying like what is the likelihood that you collected the data with this policy? Like it's the likelihood under your current policy. So like the way we learned this thing, the way we got this is we just sampled a bunch of random data, right? So the way we sampled random data is we took a state, we sampled an action from our action prior, not from a posterior, from a prior. And then you went to the next state, you got a reward, right? And so the log p hat of AT given ST is estimating the action prior. So it's estimating the policy you collected the data with. And so you collected the data just by doing random shifts. So it's estimating random shift. Yeah. Sorry, pardon my line. Okay, so what we've done here is we've said that it's equal to the product of, and William nicely pointed out that really this should be conditional on ST, so this initial state distribution doesn't need to be here, and it should really be a product from like P to capital P, starting from 0. Yeah, I should fix that. So what we're going to substitute in then is like we know that P of OT given ST and AT is equal to exponential reward, right? Which means that the product over a bunch of time steps is the exponential of sum of rewards. Right? Product of exponents is exponents of sum. Right? And so if you multiply a bunch of exponentials, it becomes exponential of the sum of results. And so you can show here that this is equal to the likelihood under the transition dynamics, the action prior times the exponential of rewards. So exponential is sum of rewards from the current time step till the end of time, right? Just by substituting the definition of the optimality variable. That's all we've done. Right? So we decomposed the joint, we substituted optimality variable. This is good. Now we've gotten likelihood of transition dynamics times the exponential at sum of rewards. Now, what we're going to do here is that we're just going to notice that this thing is now just an expectation of if you'd sampled under p hat. weighted by the exponentiated sum of rewards, right? So it's just saying that like integral P F is equal to expectation P of F, right? So you can just think of this whole thing as P and this thing as F. Sorry, I need to erase the word. This thingy as P, this thingy as F. When we say expectation P of F is equal to integral PF, right? So we're just going to go from an integral back to an expectation. Yeah. And so this just gives us the expected expectation of the expected sum of rewards. When you sample, this should really be states from your current state, actions from your action prior, and next time steps from your transition dynamics. Right? So let's get rid of that guy. But it's just saying that if you start at your current time step, you sample actions according to action prior, and then you roll things forward according to your approximated transition dynamics, right? Your numerator just becomes the expectation of exponential sum of rewards under samples drawn that. Like the same, draw samples under your model, and then weight them by the exponentiated sum of rewards. So what we've done, we started the posterior inference. We showed that it's proportional to that joint. The joint is equal to the product of transition dynamics times action prior times optimality. Optimality is exponentiated rewards, which means its product is exponentiated sum of rewards. Yeah.
Let's keep clear. So P of ATSC is like right after action prior. Should that be T hat?
Yeah, this should really be T hat, T hat, T hat, T hat, T hat. Yeah, T hat, T hat. Yeah, good call. Yeah, this slide needs a bit. Point is that you like started your current state, you sample a bunch of you sample an action, you roll it forward inside your model, and you sample another action, you roll it forward inside your model, you sample another action, you roll it forward inside your model, and then you weight it by the exponential sum of rewards of that trajectory. And so the likelihood of an action at a state is proportional to the exponentiated sum of rewards when you roll things forward through the model. Okay? And so if you look at this expression, it looks very similar to MPPI. Where in MPPI, what do? You sample a bunch of actions forward, you weight them by the exponentiated sum of rewards, then you like recompute the mean, and then you sample again. Right? And so the way to think about this kind of thing is that you've reduced the posterior computation to like rolling things forward to the model, computing the exponential sum of rewards and weighting things that way. The only difference in MPPI to this procedure is you're going to like keep repeating. So what you're going to do is you're going to run this procedure once. You're going to get the exponential sum of rewards, compute like a weighted sum of rewards, and then you're going to replace the action prior with the best thing you had in the last step. Right? So in MPPI, what you do is you sample a bunch of things, you weight every action sample by the exponential sum of rewards, and then you compute a weighted mean, and then you sample again, and then weighted mean, you sample again. Right? Same thing. The way you're going to do it here, you're going to compute the exponential sum of rewards, compute the weighted sum for this expectation, and then you're going to replace the action prior by your like, weighted sum, and you repeat again. Right? And so that's why I said the connection is a little loose. But the point here is that you can show that posterior inference is basically sampling and weighting by the exponential reward. And then you just like repeat this a bunch of times. The tricky part here is you might need a ton of samples to actually see. And the other thing that is a little bit weird here is that it's a proportionality term, which means that you have to like, if you're being completely proper about it, you have to divide it by the integral over all possible actions, which is again a pain, right? So like MPP has a lot of approximations on top of that, but this is one way to think about it. It's just like constructing the joint, marginalizing out all the variables after your current time step, and that becomes the expectation over all things in the future of the exponentiated sum of rewards, right? Which is what MPPI does. And so, yeah, so you can think of this as just say, you're going to roll things forward, remember to the P hats. But the point is you can sample actions, weight them by exponential reward, improve the action parameter. That gives you model-based RL. So all we did here is that we did a Monte Carlo approximation. We constructed a fake model so that we know likelihoods, we can sample from it, so on. And then we try to like minimize, we try to learn this model by minimizing KL or doing supervised learning. And then you try to obtain the best actions via this posterior inference through sampling, which is just say, roll out a bunch of actions in the future, weight by exponential reward, and then pick the best. Yeah, so that's kind of how you derive model-based RL. That one's I'm not as satisfied with that one as the other ones, but it gives you a way to derive different RL algorithms under the same framework. And so the reason this whole thing is useful is one, is it like when you use this framework, we talk about 3 approximations, right? We talk about variational inference with gradient descent, variational inference with dynamic programming, and then like posterior inference using sampling in an approximate model. You can design like arbitrary other approximations that you want, right? Those are just 3 approximations. So like some things that I've been excited about from a research perspective is like, can you use model-based for some part of it and model-free for some part of it, right? So can you like, for like higher level things, can you use model-based stuff, and for lower level things, can you use model-free stuff? So you can try to construct different approximations to the same posterior. Like we chose, in variational inference, we chose this form of Q, which was true model times a policy. You can also choose like other forms of Q. You can like the point is that probabilistic inference is a pretty rich field. It gives you different types of inference methods, and we should be able to apply that to our policy. So like from a research perspective, I think it's a nice tool. Okay, any questions? Okay, I guess we can end a little early today. Thank you. See you Monday or Tuesday. Yeah. I was just, because I was late to the class, I was just giving you feedback on yours.
Oh. If you have, I'd love to hear it.
I just typed it out. Let me.
Some of the stuff that you poked holes in last time. So I just kind of like left it as like, I need to find a way to.
Yeah.
Optimize it.
I think